Once again, the physics video lecture, Physics 203, video lecture 20. So let's get started. I'm going to begin with a review session for the midterm exam that's coming up later this week. And there are 4 problems, three major themes, and I'll just give an outline and review for each of those topics. So the first central point of the entire semester is the variational calculus. And I have found a very nice problem of the form variation of a function f of y, y prime x dx x1 to x2 is equal to 0. So we know if we have something of this form, we have 2 main consequences. First of all, the Euler-Lagrange equations, so d dx partial f with respect to y prime minus partial f with respect to y is equal to 0. And based on this, and in addition, if there's no explicit dependence on the variable x here, so second point is that if f is not explicitly a function of x, that's the way I always write that, then we have from Euler's second form, df dy prime times y prime minus f is equal to constant, some constant. And we've used this a number of times now. We know that when we go into the Lagrangian mechanics and actually have the physical Lagrangian up here, then this expresses the energy conservation. When we were doing Maupertuis principle, we found that there's a constant here as well. It's not necessarily the energy in that case. In fact, a little hint for what we did when we do the Kepler problem with this formalism here for Maupertuis, that constant turns out to be the angular momentum, conserved quantity there. And giving away even a little more, in the projectile motion problem with Maupertuis principle, that would have been the x component of the linear momentum. So, yeah, so we get a constant out of that. And then to continue solving the problem either with the Euler-Lagrange or with this second form here, in both cases, we want to reduce the problem to a quadrature. So I'll say here is point 3. And if so, there's an eraser. So quadrature is also important. That's where you can separate the variables. Remember, what we're looking for is y of x in the final analysis. We're looking for y of x. So you have dy over dx is equal to something. Can't say f, I'll just say some function phi. And if you can separate it, dy, whatever you can separate, equals, say, x minus x0 in that case. Okay, something in here. I'm not being explicit on this right now. This would be some function. So this would be the reduction to a quadrature, and if you can actually invert this, and then you could get y of x. So finally, if possible, go from x equals x of y, which is what we have right there, to y equals y of x. In that case, we would be done with the problem. Good, so I have a nice problem with this form, and that'll be one of them, so variational calculus. Good, the next major theme is in Lagrangian mechanics. Lagrangian mechanics. And here we'll start with the idea that we have T1 to T0. So now we applied this formalism that we had developed to the case where L equals T minus U, function of the generalized coordinates, generalized velocities, and time. Okay. So we have various and assorted applications here. The one we're going to do, one we're going to concentrate on, is small oscillations. So small oscillations, you begin with a Lagrangian of this form here, this famous quadratic form. U, okay, I'll just Q1, Q1, I'll just write it as vector. And by expanding the potential energy about the equilibrium and evaluating the kinetic energy at equilibrium, expand about Q0, and that's for the potential energy, and evaluate the kinetic energy at Q0, we end up with the small oscillations Lagrangian, for which we have a complete solution theory. So the small oscillations Lagrangian, we have replaced the Aij of Q0 by just a matrix Mij. The Q dots, x of I is q sub I minus q0 sub I. Okay. You have xi dot xj dot, and then the expansion of the potential energy ended up giving us a matrix of these constants, which are just the second derivatives of u, xi, xj. And if this matrix is M and this matrix is K, then we had finally the determinant of minus omega squared M plus K equals 0 gave us the characteristic polynomial for these omega squareds. And don't multiply it out too far, okay? Because we're obtaining omega squared here, then those go into the solutions e to the I omega sub something or other k t for the various and assorted frequencies. Now the problem we're going to have on our exam is just going to be 2 by 2, so 2 degrees of freedom. In fact, I have 2 problems for you. Each one has 2 degrees of freedom. They're perfect. They are perfect. So this and etc. So actually, to make this complete, let's even put these definitions in here so that Mij, Aij of Q0, and by the way, this is the equilibrium point, and these K components are the second derivatives Okay, the second derivatives, all mixed ones, evaluated at Q0 as well. And important to make these matrices symmetric. So both of these are symmetric. Put it here in red. And you symmetrize them if they aren't already symmetric. Good, so let's look at a good problem of this type. So we have on our x-axis a mass on a spring, capital M spring K. No friction, and we're just going to hang a simple pendulum from that mass. This one has the full richness of the entire theory. So suppose we have an angle phi right here, and the coordinate x for this mass right here. Then the kinetic energy is a half capital M capital V squared plus a half lowercase m. It's V squared, but what is this V right here? So capital V is x dot. That's no problem. Lowercase v squared is vx squared plus vy squared for this pendulum bob. So Vx, you have to take the x, actually, let's not do too much right here. So we have x and y, this is a capital X right here, okay, in uppercase. We need x and y for the pendulum bob, and that would be capital X plus L sine phi, y would be minus L cos phi. So it's only when you take the derivative of this, square them, add them up, that you can replace this v squared here. So this x dot, capital X dot, L cos phi dot, etc. So you have a bit to do in a problem like this to get your kinetic energy, and only when you've brought it down to these two independent variables, your capital X and your phi, can you actually plug that into a Lagrangian. Otherwise it's just a kinetic energy. Potential energy, you've got a half K capital X squared for the spring. Okay, good enough. And you've also got minus MGL 1 minus cos phi. For the pendulum. Okay. So this is how you got started on this one. I think we've seen this problem before. And you can eventually take it into this form here, and then you can get the frequency of small oscillations. We'll have two frequencies, 2 degrees of freedom. So when we did this, we're just assuming that the origin is taken where this spring is relaxed. Okay, I'm going to put a note here about these ideal springs. So when you have an ideal spring in a problem, it has no energy, no potential energy when it's in its relaxed state. Okay. So for example, if you have a spring here of relaxed length A, then your potential energy would be 1/2 K x minus A squared if you were to stretch it and compress it. On the other hand, if we just take the origin here to be 0 when it's relaxed, then we don't have to subtract anything off. Okay. So that can play a role as well. Good, so we have Lagrangian mechanics, small oscillations theory, and then application. And my fourth problem is we're going to have 2 of this type. The fourth problem is a central force problem. So we just need our central force formalism at hand. And remember, we started with 2 masses and the relative vector. So here was R1, R2, and R, and we had M1 and M2. And what we found was when we have a central force, we can turn this into L equals 1/2 M R dot squared plus R squared P dot squared minus U of R after a number of steps. And in that case, this mass here is the reduced mass. And we also have a way to get from the solution for the vector R back to the original R1 and R2 if we need to. We can transform back to that. The energy for this same thing turned out to look like this. M R dot squared plus L squared over 2mr squared plus U of R. And that was because angular momentum is conserved for all central forces. And then we called this the effective potential. And we just had an effectively one-dimensional problem here of the form plus U effective of R equal to E. Effective one-dimensional problem, that's why we called this that. This actually came from this term right here, which was the part of the kinetic energy, but formally we bring into the potential energy called an effective potential, so that we can just do all of our one-dimensional skills on this object right here. So yeah, I have a simple but very, very nice little problem for this as well. Good, and that's our review. Let's see how much time we have left. We've got nothing but time. Good. Okay, so now where are we? Canonical transformations is what we've been doing. And we ended with the solution of the harmonic oscillator. Harmonic oscillator has to be solved with every new technique that we develop. Good, I'll send this out. Okay, so what comes now is going to be a major theoretical development. So I'm going to put all of the canonical transformation formulas that we need up on the board and kind of remind us what they're good for. We are using the canonical transformations to solve the Hamilton-Jacobi equation. So there are many more applications of it. If you look in Goldstein, you'll just see endless canonical transformation material. We only want to use it to solve the Hamilton-Jacobi equation. So what we did last time is definitely a proof of concept. We had to show how that worked, and it did work. So let's go ahead and write down everything that we need for this next development. And the idea was we were going from a set of Q's and P's to a set of Q. So from, in a Hamiltonian system, from coordinates and momenta to new coordinates and momenta. And the point was that we had a lot of freedom here, because we have two n variables. And so the new variables are just uppercase of the old variables. Q1 to Qn, P1 to Pn, and T. And we can do this because the sets of coordinates and momenta are all independent. We always have 2n of them instead of just n. And in order to effect a transformation like this and still have Hamilton's equations hold true, we had to have a couple of conditions here. So yeah, I'll go ahead and write down, we had sum of p I qi dot minus h q p t. So that was the Lagrangian. And this is going to be the new Hamiltonian, we'll call it K. And for these two objects to be equivalent, they have to differ by a complete time derivative of some function of any combination of all these coordinates, old and new, because they're all coordinates. So the conditions for this depended on the choice of the arguments for this generating function. Play a big role, the generating function. And I'll just write down the two types that we're going to use. So for F1 equals F1 Q old coordinates, new coordinates, and time. Then we had the conditions. Make sure we get these. Actually, I want to make this more complete. Yeah, so before I write those conditions, remember for this Hamiltonian here, we of course had Q dot is equal to dH dP and P dot minus dH dQ. Okay, so those were the canonical equations for this side. And the canonical equations that we're looking for are going to have to be the analogon here, so we're looking for Q dot is equal to dk, d dot, all uppercase now, P dot is minus dk, dqi. So this is what we are requiring. Okay. The whole point of this exercise. Okay, good. So what do we have here? For these we had P sub I is the F1, Q sub I, and capital P sub I is minus the F1, capital Q sub I. These are the relations we used to solve the harmonic oscillator last time. Good, so this needs a box around it. This is the one, oh, and df1 dt is equal to k minus h. So these are the relations that we had available to us. Okay, now we use these for the harmonic oscillator, so that's an example. It's right out of Goldstein, but it has all of the ingredients that we need. And we're definitely using this as a proof of concept for what follows. So the other type that we're interested in, and there is a large number of extra possibilities in these generating functions. So the second type of generating function, Q, P, and T. So old coordinates, new momenta, and time. Then we get the results P sub I, D, F2, dq sub I. And then we get this relation, Q sub I is equal to df2 dp sub I. Okay. The f2 is a function of the old coordinates, the new momenta, and so that's uppercase, that's lowercase. And for all of these, we have df2 dt equals k minus h. Okay, this one, by the way, was assigned as a homework problem. You had to Legendre transform this F2, and then these came out right away. So that was not difficult. I wanted you guys to do it because we're going to, it was a good review, plus we're going to use this. So possibly I actually did it. Forget. But anyway, it was a homework problem whether I did it or not. So just get these relations here. Okay, trying to have everything on the board at once. So there was the canonical transformation. And then I'm going to write here, recall or work with the Maupertuis principle. Etc. We had the idea that if we define S, actually not so fast. If we just interpret S as a function of the upper boundary of our Lagrangian. Remember before when we were doing variational calculus, we had fixed boundaries, and then we just got the Euler-Lagrange equations out of this. But if we consider this as a free upper boundary, then we had P sub I is ds dq sub I. energy is conserved, we had S equals S naught minus E times T, where S naught was the restricted action. That's where we got to the principle of Moore-Tui's. And ds dt plus h equals 0, or I could write equals minus h. So yeah, let's put a box around all these as well. Actually, let me say a little more about this. So these are all the developments we've had. This was the abbreviated action. This was the Hamilton-Jacobi equation. So we had all of these relations. And what we're looking at then is S as a function Q1 to Qn and T that satisfies this equation right here, or S equals S naught of Q1 to Qn minus E times T if the energy is conserved because of this abbreviated action relation. If the energy is conserved, you take ds dt equals minus h, which is E, right? So minus E. So S naught Q1 minus E T. And for these relations, got room here? Yeah, squeeze it all in. ds dt plus h of Q1 to Qn ds dQ1 ds dQn and T. Okay. So this is the Hamilton-Jacobi equation, partial differential equation, with a comma right there, because the Hamiltonian's a function of Q and P, but if you have this relation here, which one? This one right here, P is ds dq, then you can replace all those with ds dq, and that's why this is a partial differential equation. We had written that down before and we will again, but we had written it down for a simple system just to write it out explicitly. So we have all of that, and now what we're going to do is combine all these things. Namely, the problem was how to obtain the motion of the system from this equation here. And we didn't have the ingredients for that when we first obtained these equations. So how to obtain the motion of the system, which is Q of T. Q of T from the Hamilton-Jacobi equation. So that's what we're going to do now. Good. Yeah, we've got time. This is good. Okay, so we want to obtain the motion of the system. This is a new formalism. So what we have to do is solve a partial differential equation of this type, which has its own techniques that we'll study. And then if you can solve this equation, how do we obtain the motion? And we're going to use everything that's up on this board, so I can erase this one here. Okay, let's see what we have here. We have the relations pertaining to the canonical transformation right up here in the blue box. And then this is where these derivations came from. Then what we have is this differential equation. Yeah, all of these things pertain to the Hamilton-Jacobi equation. And just to remind us, example, and we'll either solve this now or next time, the harmonic oscillator, for starters. So for the harmonic oscillator, we know energy's conserved, so we're going to make use of this relation right here. Well, let's remind ourselves. Harmonic oscillator has the Hamiltonian p squared over 2m plus 1/2 k q squared. Okay, so there's a Hamiltonian, and h equals E is constant. We know that as well. So the Hamilton-Jacobi equation is going to be ds dt plus h of q, won't have an explicit time dependence in here, right? So plus h, but this is h, so plus, we'll put parentheses around it just for the heck of it, plus 1 over 2m ds dq squared plus 1/2 k q squared, okay, equals 0. So that's what we're going to have to solve. That would be an example of the Hamilton-Jacobi equation. And in fact, since S equals S naught minus E times T, we could even write this. The ds dt is going to be minus E. Okay, so I'd have a minus E plus this equals 0. So I can actually take it one more step and write, I'll bring the minus E to the other side, so I'll have E on the other side, so I'll have 1 over 2m ds0 dq squared plus 1/2 k q squared equals E. Okay. So that's what we would do because we have conservation of energy. And S equals S naught of Q minus E times T when we're all done. So yeah, we're going to have to learn to find this from this. In this case, it's not easy. It's not difficult. Solve the partial differential equation. We'll set it up. We already set it up. But we don't yet know how to obtain the motion from it. So that's what the rest of the board is needed for. Okay. Okay, so the trick we're going to use, so to speak, is we're going to interpret this function S that we found by hook or by crook, okay, as the generating function of type F2. So to find the motion, next, having obtained S equals S of Q1, Qn, and T. Oh, and I should actually have to say, this is the solution to the PDE, the partial differential equation. Therefore, we've obtained it as S of Q1 to Qn, and then alpha 1 to alpha n. In other words, there are n integration variables for this partial differential equation. of n variables, comma, where the alpha 1 to alpha n are integration constants. Very important that they're constant, okay? They're integration constants. So this is the solution we actually obtain. We get something in this form right here. And now what we do is we interpret this as a generating function. So having obtained that, we take S to be a generating function. S of Q and alpha and T. Notice I'm just writing these as the vectors, n components of alpha and T is equal to F sub 2 of Q capital P and T. This is the trick. What follows is pretty amazing. Okay, so this is a function of n variables here and these n integrating constants in time, and we say, okay, that's the generating function of a canonical transformation of the Q's, the new momenta, and the time. Yeah, this is the key statement right here. This is a generating function. Now I'm going to leave these up here and erase everything else. So what we have is the Hamilton-Jacobi function is a differential equation that gets us a generating function of a canonical transformation. So let's see what that does. Generating function of a canonical transformation. Okay. And it's of this type, so this is up on the board as well. So now what do we have? I think I'm going to do 2 columns here. Because we're going to introduce some new letters, but they mean just, if you're going to introduce new letters that mean this. Okay, let's see here. So actually, since everything's up here, I can just do my new letters right now, right under here. So this is, right underneath here we have S of Q alpha and T. So here we would have P sub I lowercase ds dq sub I. Of course we had that before, right? We know about that. Then we would have this relation here, I'm going to save for a moment. And what do we have here? We have ds dt is equal to k minus h. Okay. Saving this because we're going to rename the cubes. Okay. So let's just focus on this right here. Okay. So what do we have? We have the Hamilton-Jacobi equation. Is it up there? It's been erased. We have ds dt equals minus h. Okay. So what that means is k is identically equal to 0. Okay. So if we're making our comparison, our Hamilton-Jacobi equation ds dt equals minus h. So k must be identically 0. So K is identically 0, but remember, K is the Hamiltonian of the new coordinates and momenta. So we have Q dot is equal to dk dp. Let's write that down. dk dp, put an I there. And p sub I dot is equal to minus dk dq sub I. Remember, that's what the whole canonical transformation is about, making sure that you still have Hamilton's equations here. Okay, but what do these equations mean if the new Hamiltonian is identically 0? I'm going to put this in words. The new Hamiltonian identically 0. Couple exclamation points for you. Yeah, what does that mean? Well, these equations still hold. That means that Q dot and P dot are all equal to 0. What that means is Q and P are constants. Okay. So, important here, Q sub I is equal to constant. And now we're going to give it a new formal name. We're going to call them beta sub I. And P sub I are constant, and we're going to call those alpha sub I. Those are the alphas that we already found up there. Okay. So always the most important line here in the bottom right-hand corner. Okay. So the new coordinates and the new momenta are constants. By the way, if you go back to Hamilton's equations, what does that mean about the new Hamiltonian? Okay. If all of these new coordinates, if the new coordinates and the new momenta are constant in the Hamiltonian, it means that this new Hamiltonian K has only cyclic coordinates. So we found a way to get all cyclic coordinates. Okay, that was kind of the theme of this thing. How do you find all cyclic coordinates? So every coordinate here is a conserved quantity in this set of, in this new coordinate system. Okay, so we have enough room on this board to make use of that. So I'll put this in words. Actually, now I'll fill in. Okay, I'll fill this guy in here. So, and we have the beta sub I is equal to ds d alpha sub I. Okay. So this is right directly translated into our new variables. If we solve the Hamilton-Jacobi equation and take S as a generating function, we find that the new Hamiltonian is identically equal to 0. Therefore, the new coordinates and the new momenta are all constants. Okay. So now we can draw the conclusion from this. New coordinates and momenta, and that is our, Q's and capital P's, but now we're calling them beta and alpha. So Q beta by definition, P are these alphas. And so the method of obtaining the motion is actually already here. Namely, this equation here, when all is said and done, because betas and alphas are constants, this set of equations here, these n equations, are algebraic equations. Okay? They're no longer differential equations, they're algebraic equations. So beta sub I equals ds d alpha sub I equals 1 to n are algebraic equations. And that means if you can, okay, here, I got a better way to write this. Since this is a punchline here, we have enough room yet. So what we're just going to do is write the arguments in here. Q sub 1 to Q sub n, alpha sub 1 to alpha sub n and t. Okay, this is the punchline. So these equations, or n of them, they are all algebraic equations. So if you can invert these equations, then you would have q as a function of t. Okay. Beta sub I are algebraic equations. Invert to obtain q of t. Okay, I'm going to check the time on this. Okay, fantastic. Okay, I'm just going to say a little more about this. And because, you know, we go through this big development here, which isn't as involved as it seems. But the point is, when you've done this in a whole interpretation, that's a canonical transformation, etc., when you get to this point, you have a recipe for solving problems that no longer requires this canonical transformation. We did it once, or interpreted it that way. So all of this development here, it's not to be forgotten, by the way, it's important, but when it comes to solving problems, the technique, the procedure is not that long, because we did all of these things and we came up with a solution method. So I think what I'll do is write that down, just so we, so we're not blinded by all this other stuff. And I will leave this up. I'll send this back up because we can use the harmonic oscillator as an example. Okay, I'll erase this stuff and then just put it down in the essential result that we've obtained here. And then that'll require its own set of techniques to go through, but the basic result is not complicated. Okay, so what does the Hamilton-Jacobi method reduce to? So in 3 simple steps. Hamilton-Jacobi method. So first of all, we would say we have our mechanical system. We have to go through the whole process. Kinetic energy, potential energy, Lagrangian, Hamiltonian. Say, but I'll just say you've got a mechanical system, and you have to bring it into the form of H of Q1, Qn, P, and T, right? We need a Hamiltonian. Good. So the next step is to write down the Hamilton-Jacobi equation, which we know is ds dt plus h of q1 to qn. Now remember, we were replace the p's with ds dq1 dqn and t equals 0. So that's the partial differential equation that I have up on the board for the harmonic oscillator. Okay, so we've made that substitution. And I'll just note, if E is constant, which is to say if H is not explicitly a function of T, so if the energy is constant, then S equals S naught minus ET, and H of Q, I'll write this in shorthand, ds dq as a vector is equal to E. That would be the Hamilton-Jacobi equation of this form. Okay. Good. So the third step is that we have to solve and obtain S is equal to SQ, I'll write them all out, Q1 to Qn, alpha 1 to alpha n, and T. Right, so that's the solution technique we don't yet possess for most cases that we're going to have to work our way through. But if you find this, then beta sub I is equal to ds d alpha sub I equals 1 to n are algebraic equations. They're no longer differential equations, and if you can invert them, invert to obtain Q of T. Boom. Now, if you can't invert them, what you're generally doing is reducing these equations to a set of quadratures. Okay. And that's not a contradiction to these being algebraic equations, because you go a step back and you've expressed the thing in terms of quadratures. Okay. In other words, your S is reduced to a set of quadratures, okay, from which you can then get these relations right here. Okay, so you know that's probably a good place to call it a day. But yeah, we have everything up on the board we need. I'm going to write a couple more things in here. So solve, obtain this, or, oh, by the way, yeah, here, good, we can fill in. If we're doing the conserved energy version with S sub 0, then this is S sub 0 in there. Okay. So when or we would have S equals S sub 0 Q and alpha minus E times T. Yeah, you have one or the other, but this here is the big result, and it has your solutions Q in there, right? Q and alpha, and if you can invert them, then you can get Q of T. I could write this one more time. So you've got your beta, in fact you could write it this way, beta vector is ds d alpha vector. It's just a way to say we have all n of those equations, Q, alpha, and T. So that's equal. So if you can invert this set of equations, this set of n equations, you can invert them, then Q of T could be teased out of that. That's the idea. But we'll get there. Okay, we'll get there next time. So what we'll do next time is write, a fair amount of this back up on the board, but then we'll tackle the harmonic oscillator Also just as a proof of concept, and then we'll start talking about how to deal with the various and assorted interesting cases. Okay, good. See you next time.